Right, something went wrong with the recording, but right, this is what we're expecting. We're expecting this sort of field for this. So let me just draw another line in. So look, I'm expecting to draw a line from here, from the north to the south. I'm going to make sure none of them touch. So that's what I'm expecting, yeah. Let me just draw one on this side. So it'll go from the north to the south. Nothing's going to touch or cross over. You can get away with it touching at this end because it gets a bit tight. So that's the magnetic field we're expecting. Remember we said like poles repel. Repel the force, the push away from each other, not pull, the push away from each other. Right, give a reason why the two magnets shown in the diagram will repel each other. Why will they push each other away? Is because we can say like poles repel. Complete the diagram by drawing the shape and direction of the magnetic field pattern between the magnets. So that's what we've drawn here in this region, yeah. So that's what they're expecting. So remember, the lines do not overlap here. They do not cross here. Right. Right, so now we've done a... Ooh, I chopped away question B. Okay, so I'm just guessing now here that this is made out of plastic. Because that's plastic, it is not magnetic. So it won't be involved in anything, right? It won't affect anything. Right, okay. In the position shown, the balance reading is 1.6. Explain how the balance reading will change if the magnet A is brought closer. So what's going to happen is they want to move this magnet further down, yeah. So you get that and you move it further down. Now when you move it further down, because the magnetic field's closer, it's going to provide a bigger force pushing down. Right, so what'll happen is this force here, the 1.6, will increase. So what can we say? It's a 2 marker. So we can say the reading on the page will increase. The reading will increase. The reading will increase. Second mark, because the reading will increase because the magnetic field, or the repulsive magnetic field, force field, oh, let's use the word force will be stronger. Right, because it's closer, it's going to have more of an effect. Right, next question. Explain how the balance reading will change if the poles of magnet A are reversed, but the distance between the magnets remains constant. So what happens? They're going to turn this around. So what's going to happen is that there will become south, and that there will become north. Now we can get rid of these. Let's just get rid of all this. Get rid of all this. Right, now what they're going to do is they're going to attract from north. Remember what we said, it goes from north to south, from north to south, from north to south, from north to south. And it'll be a attractive force. Attractive force. So what's going to happen is this, because this is stationary here, this does not move. This will move up. So this force here might go down to just say 1.0 newtons. Right, so now we need to write that. So we can say the reading will decrease. The reading will decrease or get smaller. Why? Because the magnets will now attract. Right, give a reason why the top plate of the balance is not affected by the magnetic. Oh, silly person. That should have been there. Is not affected by the magnetic fields of the magnet because it is made of non-magnetic material. Right, or I could have said it is made of plastic, which is non-magnetic. Right, okay, done. Interesting question that was. Right, question number 8. What we're saying is a uniform magnetic field, right? Is produced in the space between the magnets. So what will happen is this will be north, because it's where is it uniform. Right, remember we did this on the previous one. These lines are straight, so you get a ruler and draw, oh my word, straight lines, same distance apart. I'll eventually get there. And finally, yeah. So first thing, the same distance apart here, okay? Then the magnetic field always goes from north to south, so the arrows are going to be. So look, 3 things that we learned previously. It says the lines are straight. It's good to keep going over this, so when you sat there stressed out a bit, you'll be able to recall it better. Lines are straight. Lines are, starts with the P, parallel. And then lines are the same distance apart. Right, let's carry on. Right, another let me get this right. Diagram 2 shows another neodymium. Wow, neodymium. I don't know what that says. Magnetic material, magnet being used to lift an iron ball from a table. The iron ball is shown at the instant it leaves the surface of the table. Explain why the iron ball experiences an upward magnetic force. Right, why does it do that? Oh my god, did I just go straight to... Yeah, we've done that. That's part A. We're on part B. Right. The iron ball is a what? A magnetic material. Yeah. The iron ball becomes magnetized. Right. And then so you've got a north pole on this ball here now. Then the ball is attracted to the magnet. Right, okay, we've done that. Let's move on. The iron ball experiences an upward resultant force as shown at the instant shown in the diagram. Draw labeled arrow on diagram 2 to show the way of the iron ball. Right, let's get rid of you. Right, just pay attention to this. Look, you see how long that is there? We want to draw a line shorter than that because it's going to be pulling upwards. So from the center, that there is the weight. And we know weight is mass times gravity. So we just want a downward arrow shorter than the magnetic force drawn. What they're saying is this red line has to be smaller than the black line. Right, okay. State a formula linking weight, mass, and gravitational field strength. So we know weight equals mass times gravitational field strength. It's best to write it all, I think. It's best to get used to the whole thing. Right, okay, at the instant shown in diagram 2, the resultant force acting on the iron ball is 124 Newton meters, and the magnetic force is 165 Newton meters. Calculate the mass of the iron ball. So what they're saying is the upward force is 165, the downward force is 124. So calculate the iron ball. So what we want to do is work out 165 minus 124 equals 41. Right. It's a 4 marker, so what do they want next? Let's have a look. So we worked out the overall force, so we know the weight is mg. So now we know is that's 41 millinewtons, so it'll be 41 times 10 to the minus 3, or I can write it as 0.041 equals, right, mass, and then we know the gravity is 10. So remember, we write it like this and then we rearrange it. So m equals 0.041 over 10, which equals 0.0041 kilograms. So that was in millinewtons. Milli being divide by 1,000, or it means 10 to the minus 3 times by 10 to the minus 3. Right, explain why the resultant force acting on the iron ball increases as the iron ball moves towards the magnet. Right, what we're going to do is we're going to get a pen and start here. Right. Since the weight of the ball is the same, the magnetic force increases since the magnetic field strength increases. So what they're saying is this: as the ball, so look, so these are the magnetic field lines. As you get further away, they get further apart, so it means it's a weaker. Let me get hold of this. Right, it's a weaker field, but as it starts going up, it cuts more of these, so that means the attraction or the magnetic field is stronger, so it'll have a stronger pull, so the force attracting it will be even stronger. So that's what's happening. Look, so it's going from there, it's further away, it's weaker. As it starts moving up, it gets into this more dense area and the force increases. That's all you've got to know. Right. The diagram shows a bar magnet. Draw 4 magnetic field lines around the bar magnet. So we know it goes from north to south, so it does this. Yeah, so it does that. Whoa, where did that come from? Whoa, what's going on, dude? Right, 1, 2, 3, 4, and then it goes from north. Just get into the habit of drawing from north to south. So in your head, you know it's going in that direction. Right, there you go. The key thing is, look at this, that they're not crossing over, they're not touching, and it's going from north to south. Right, the diagram shows have I drawn enough? No, it's saying 4. I've drawn 2 on each side, so I need to draw another one. It goes that way, and let's draw another one here. It goes that way. You have to be careful. Be very careful that you don't cross over anywhere. Right, you've got to be very careful. North to south, so let's just draw it there, safer. And then finally, if I did a green one, 1, 2, 3, 4. Yeah, I'm going to make sure it doesn't cross anything. Make sure it doesn't cross anything. Careful when I get down to here. There you go. That's it, done. How easy was that? Right, the diagram shows a loop of wire connected to the terminals. You've got a voltmeter, and there's the wire. So there's a magnetic field, whichever direction it's going, it doesn't matter. And they're not crossing over here. They're not crossing here. We'll pretend they're not crossing. So can you see, when you move the wire, you're cutting through the magnetic field here, which will induce a voltage. Explain why the voltmeter changes from 0 when the magnet is moved near the loop of the wire. Right. Simple, yeah? The metal wire cuts the magnetic field lines. Let me write that fully. Magnetic field lines and induces a voltage. And induces a voltage, or causes an induced voltage, same thing. Right, okay, let's move on. Yeah, the last question really. Right, we've got I think that's it. Oh, I should have used that actually. It doesn't matter, it's done. There was a speaker question attached to it. But let's carry on anyway. This question is about a radio powered by a person turning a handle. The radio has a battery which stores the energy when the handle is turned. The diagram shows the part of the radio called a generator. The generator produces voltage which does electrical work on the battery. Right, so basically what happens is you've got a magnetic field here, and then you've got this coil here, and when that rotates and cuts the magnetic field, it induces a voltage, and because you've got a circuit, it produces a current. The current then goes to the battery and is stored. Now, how do we put that in words? Right, so first of all, the handle is rotated, making the coil turn. The coil cuts the magnetic field lines off the, this here is a it's a permanent magnet. Field lines off the permanent magnet. There you go. That's it. There was another question attached to this, but it's not there. I think that was it. It doesn't matter. It's a shame that. Right, done. End of magnetism. Finally. Made me ill. I'm gonna take a few days off now.